First thing we're going to do is write down all of the knowns that came from the problem. So the problem explicitly stated the dipole moment to be 6.1 times 10 to the negative 30 coulombs times meters. The electric field that the dipole exists in is 2.0 times 10 to the fifth newtons per coulomb. And we have three questions. We have part A, which they ask what is the maximum torque magnitude. Part B is what is the potential energy when the torque is maximized. So the same orientation of the dipole in part A is going to exist in part B. And then for part C, in what orientation is U maximized? So maybe U is going to be maximized the same as the orientation in part B as in part C, or it's going to be a different orientation. We don't know yet. So for part A, let's go ahead and look at when torque is maximized. First, let's look at what the dipole looks like, and then kind of check out the definition of a torque. And this is just the magnitude of the torque there. So we can say that torque is force cross R. And the orientation that works best, I believe, is the vertical orientation. And let's see why that is. So a force is going to act on the positive charge up here, going towards where the E field is going to go. Force is going to act on the negative part of the dipole here, going in the opposite direction. Now, this orientation, I think, is the maximum, produces the maximum amount of torque. This orientation could also be a pretty good candidate because it's furthest away from where it wants to be, and the negative side is also furthest away from where it wants to be. But the problem with that is that it's going to want to bring the positive charges straight over to the right and the negative charges straight over to the left. It does not produce any rotation. It more like produces a squishing effect. So we basically conclude this vertical orientation is going to produce the most amount of torque. So that being said, if this dipole has a length of S, let's just say, then the force produced from this charge distribution going in this direction based on the center of mass of the dipole, which we'll assume it rotates about, is just going to be force times S over 2. That's going to be half the length of the dipole because the force is acting, let's just say, on the very tip right here, S over 2. And it's going to be perpendicular because the force is going to go this way. The radial vector is going up. So this actually works out pretty well. In terms of E field, the force is going to be Q times E, as we might have discovered earlier. We're going to carry over the S, divide by 2. And what we're going to now look at is the fact that this is going to happen twice. There's going to be another torque on this side of the dipole going this way under the radial parameter of S over 2. So essentially what we're going to do is we're going to have to multiply these both by 2 in order to make this give us the total torque acting on the dipole. So these 2's cancel out and we get Q, E, S. Now, based on the definition of dipole, P is equal to Q times S. So we can say that torque is then equal to P times E. And since we know the orientation is beneficial to getting rid of the cross product and dot product, we could just say that this is the magnitude, is just P times E, no worrying about the vectors or the how they multiply. This ends up being, if you were to calculate P times E, it would be 1.22 times 10 to the negative 24 Newton meters. Okay, and that's going to be the torque acting on the dipole at the maximum orientation. Now for part B and part C, I'm going to do over here. For part B, we want to know what the U is, or the potential energy is, when torque is maximized. So we already know what the orientation is going to be. It's going to be, again, positive on top, negative on the bottom. E field, let's just say, goes to the right. And then we'll go ahead and say that phi, which is a angle of orientation, is just going to be 90 degrees. Well, based on the derivation of potential energy ends up being negative P E cosine of that phi right there. And the reason how we came up with this derivation was we just looked at work is equal to force times distance, or you can basically say work is equal to, if in calculus version, force dx, and also equate it to the change in U. So once you look at how force acts on a dipole, plug it in here over some sort of distance, you're going to see some sort of delta U come about in the derivations. And the delta U ends up, or one of the U's in the delta U ends up being negative PE cosine phi. So that's how the potential energy is derived. Well, since phi in this case is 90 degrees and cosine of 90 degrees is 0, the U ends up being 0 for this problem. So this actually ends up being pretty trivial. That being said, I mean, just looking at this equation again, you want to look at U max and you want to see what the orientation is. Well, U in general, again, is just going to be negative PE cosine phi. And we get to just kind of figure out what the orientation should be and to maximize U. Well, we know when cosine is 1, U is the most negative. It's going to be negative PE. When cosine of phi is 0, then we know that U is 0. So that happens during this orientation when phi is 90 degrees. But when cosine of phi is negative 1, this U becomes maximized at positive PE. And cosine of phi is negative 1 when phi is 180 degrees. So just from analyzing this equation, we see that the orientation of the dipole is going to be 180 degrees from when the dipole is at positive end over here, negative end over there. And that means it's just going to flip 180 degrees like that. So this is the orientation to maximize the potential energy. And that's the answer to this problem right here.